Hello there UILCS coders. In this video we're going to be covering the binary search tree in Java. This is the first of the three trees we're going to look at in this course, or in this series. The binary search tree, I guess we can start off with the definition. I have it defined as a data structure that connects nodes, and I could probably do like a period here, or put this in parentheses, right? So Stencil is a data structure that connects nodes, with smaller nodes being connected to the left and larger nodes being connected to the right. Now what do I mean by this? Well, you're familiar with the idea of a node and how it has pointers, how it stores data and has pointers. If you've watched the linked list video. Now in the linked list video, we had data here and then we had a next pointer that pointed to the next element, right? Or the next node's memory address. It's the same idea here, except now we have a left pointer and a right pointer, okay? And then so when I say that smaller nodes are connected to the left and larger nodes are connected to the right, this is kind of what I mean, right? Look, we have 30 in here, so a smaller node like 20 would be connected to the left of 30, while a larger node like 40 we said to be connected to the right. That's not good. Left, then right. We said that larger nodes should be connected to the right, right? So you can see here through the right pointer we have 40. And this pattern kind of holds true for all of these elements, right? Looking at 20 now, a smaller node like 10 should be to the left of 20, which it is. And then a bigger node like 15 should be to the right of 20, which it is. Or sorry, this shouldn't be 15, this is wrong. Because is 15 bigger than 25? No. I'll make this 25. So now the condition holds true, right? Large nodes to the right, 25 is greater than 20. Right? Same here, 35 is less than 40. It's a smaller node, its data is smaller. So it'll be with our left pointer. And then 45 is larger than 40, so it'll be connected by the right pointer. So before we dive into this, let's go over some terminology that you need to know when regarding trees. So this is what we call the root node. If you remember actually I don't know if I used root. I might have used head or something in the linked list video. Or no, that's a bad example. Okay, anyways. The root node is essentially the first node that gets inserted into our binary tree, or the top node. For now, you can just kind of look at it as the top node in the tree. Right, this whole structure is what we call a binary tree. This node, like 20 for instance, can be called the child of 30, and 30 can be called the parent of 20. Okay, so I just brought up these random terms like parent and child. Let's actually talk about that a little bit more. So when I have 30, this is 30, right? And it holds this value, this data. And from this, its left pointer points to 15. Let's just use some example, or let's use the example I have written. So it points to 20 and 40. So its left pointer points to 20, and its right pointer points to 40. So we can say that 20 and 40 are the children. Holy, I cannot write, bro. The children of 30. Now we can say this. What does this mean? Look at 20 and 30. They are directly connected from 30, right? 20 is the direct left pointer connection, 40 is the direct right pointer connection. That's what it means to be a child of a node. You're directly connected to it, or like your parent is one above you, kind of, right? And so conversely, like I just said, we can say that 30 is the parent of 20 and 30, or 20 and 40, right? So essentially, to summarize this, a child is a node, or the child of a node is the node that is referenced by its left or right pointer. So 20 is the child of 30 as its reference, as 30's left pointer leads directly to it. 40 is the child of 30 as 30's right pointer leads directly to it. And then the parent node is the node that, or essentially, how to describe it? As you could say, like the opposite, right? So if 30's left pointer points to 20, then, or here, the parent is the node that's pointer points to this node, right? So we could say 30 is the parent of 20 because 30's left pointer points to 20. 30's parent, if 30 is the parent of 40 because 40's left, or 30's left right pointer points to 40. And I was pointed out is kind of confusing. I'm using it to reference this back to linked list, something you should know. But really, you can just kind of view it as this is the parent because directly connected to it is its child, right? The children of a node are the nodes directly connected to it. That's really what this comes down to. Okay, cool. So yeah, parent, children. So arrow here showing that's children too. Right. Let's go over some more terminology. In particular, we can call this child the left child because it's connected by this left pointer, and this child is the right child because it's connected by this right pointer. These bottom nodes here, we call them as leaf nodes. So these are all leaf nodes. Leaf nodes are nodes. Leaf nodes are nodes that have no children. No children. Or conversely, we can say degree of 0. So degree 0. Now, yes, these are leaf nodes because look, they don't have any children connected to them. If you have pointers, there are pointers, but they're just referencing null right now. There's no actual value here, right? And then what is, I bring up degree. What is degree? Well, degree is the degree of a node equals number of children of node. So, right, if it's not getting into this definition that much, just a bit here. Let's just take this. Or I want to take all of it. Let's put it like right here. Right, the degree of a node is equal to the number of children a node has. So 30, we could say has a degree of 2 because it has 2 children. 20 has a degree of 2 because it has 2 children. 40 has a degree of 2 because it has 2 children. 10, 25, 35, 45 have degrees of 0, right? Because they have null children. Okay, cool. We could talk about, there's a few more that I want to cover. So there's a concept of levels. Level is like this. So if I were just, this is the first level, this is the second level, and this is the third level. And you would keep doing this, like counting or you keep counting, doing this process for however big the tree is, right? You kind of view it as counting the nodes. You kind of view it as counting the amount of nodes from the root to a leaf, right? We have 1, 2, 3 nodes from this leaf, from this root to a leaf. If you wanted the level of 20, well, that'd be 2, right? As indicated by this line here. But you can also just get it by counting from the root to that node and seeing how many times, or sorry, you can also get it by just counting how many nodes you pass from going from the root to that 20, right? So this is 1, 2, okay, we're here. Like 10, right? 1, 2, 3, then we're here, right? So you can view it with this or just the counting, whichever way helps. Now, here is the idea of height. Now you can view height, if you understand levels, height is just the level minus 1. So at 30 we have a height at 0, at 20 and 40 we have a height of 1, and then here we have a height of 2. And this makes sense, right? When we're just looking at 30, right? When we're looking at just a singular node, how can this node have any height? It has no children or anything, right? It's just a node. You could also view it as the number of edges, which are these lines, to a node. So the height of 40, how many edges are from root to 40? 1. Height of 45, how many edges are from root to 45? 1, 2, 2. Those are height and levels. Leaves, I explained children, I explained parents. There are some concepts like grandparent is, if this is a parent, then the grandparent of 10 is 30, is the parent of the parent. Concepts such as siblings, so siblings are, should write sibling, node with nodes with same parent. There might be a better place for me to write this definition, but I want to keep everything near each other here. Maybe what if I took this sibling, paste it here. This is where we're talking about children and stuff. So, excuse me, right? So when we're thinking about siblings, 10 and 25 are siblings because they have the same parent, 20. 35 and 45 are siblings because they have the same parent, 40. 20 and 40 are siblings because they have the same parent, 35. And then some more concepts. The descendants of a node are all the node that branches off of it, right? So 30 has 1, 2, 3, or has descendants 20, 40, 10, 25, 35, 45, because all these nodes are branched off in some way from 30, right? Now 20's descendants are 10 and 25 because they're branched off from 20, but if I had another node here, like 7, well, now this would also count for the descendants of 20. So you'd have 10, 25, and 7. So it's pretty much starting at 20, all the nodes that come below it. No, 35 is not a descendant of 20. There has to be some way, like with 7 here, to, if you follow this pointer line up, to get back to 20. That is what makes you a descendant. An ancestor, on the other hand, is essentially any node that you cross on your direct line up to the root. So 7's ancestors are 10, 20, 30. 35's ancestors are 40, and then 30. I don't know if the root counts as an ancestor. I'm going to say it does. What are ancestors and descendants? Don't think that 7's ancestors are 10, 25, 20, 30. No, ancestors are just a straight line from your node two roots, so it'd only be 10, 20, 30. The descendants are different. The descendants are all the all the nodes. They're kind of offsprings from your line, right? 20 has 10, 7, 25, right? These nodes 10, 7, 25 were all created or all connected to this 20, right? You can find a way to get back to 20 just by going up from these nodes. Hopefully that makes sense. Those are the terminologies I want to discuss. It makes you understand children, parents, levels, and height, and then root and leaf nodes. Now we have that out of the way, we kind of understand the idea that a binary search tree, its main thing, a special thing about it is that smaller nodes to the left and larger nodes to the right. Let's talk about inserting elements into a binary search tree. So insertion into a binary search tree is very simple. So let us say I have this tree, right? And this is possible, right? Let's have a tree of 15, 10, then 8. And here I have 20, 25. Does it look the same as this tree? No, it doesn't. But does it meet the criteria of a binary search tree? Yes. All smaller elements are connected with these left pointers. All larger elements are to the right, smaller elements to the left. This is a valid binary search tree. Okay. Now if I wanted to insert, let's insert 18 into this binary search tree. So first you start at the root. So we're going to take this 18. We're going to compare it with the root. We're going to compare it with this element. Is 18 bigger than 15? Yes, it is. So we're simply going to move along this way. And now we're going to compare 18. So I'll copy this. We are going to compare 18 to 20. Is 18 bigger than 20? No. So next we're just going to take this and compare it. How do you rotate something? I guess rotate, flip horizontal. Ooh, that literally says 81. Leave it at that, right? Now go. So we're gonna go from here to here now, right? We're looking at the left child of 20. Well, remember that even though it looks like nothing's here, really there's null here. And in a binary search, when we've reached null, that means good. No element there, let's just take this 18 and insert it there. So we're simply going to replace this null value with 18. So I will just draw the 18 out so we don't have that weird white stuff going on. 18. Okay, let's insert 0 into this. Okay, so same idea. Now delete all this 18 references because it'll get a bit confusing, I feel like. Is we're going to compare this 15 to 0, right? Is 15 greater than 0? No, it's not. It's less than 0. So we're going to look at this left path. We're going to compare 10 to 0. Is 0 greater than 10? No, it's not. So we're going to again compare with this next left element, 8. Is 0 greater than 8? No, it's not. So we're going to compare with the next left element, which is null. And we said when we've reached null, simply just insert, oops, wrong button. We're just going to go here and take that 0 and insert it right there. So this is the general process of insertion. I'll do one more. Let's say we're going to insert 12, right? So rinse and repeat. I don't know if it makes this ratio bigger. Oh yeah, okay, cool. And that's slow. Like this, it's probably faster. And then I can just use the eraser to finish off anything remaining. Okay, so let me tighten this up. Now let's say we're inserting 12. Okay, compare 15, or I'll draw it right here. So compare 12 to 15. Is 15 greater than 12? No. Is 15 less than 12? Yes. So we're gonna compare 12 to 10. Is 12 greater than 10? Yes. So we're gonna compare 12 to this, which is a null value. And remember, we've reached null, so then this simply means just take the 12 and insert it here. So I will take 12 and insert it here. Now, key thing with binary search trees, you can't, no duplicates are allowed. So no duplicates can be inserted, and then also no nulls. So what does that mean? Let's say I tried to pass in 15 again. Well, compare 15 to 15. Is 15 less than 15? Here, let me clear this up before I get to that. Okay, is 15 less than 15? No, it's not. Is it greater than 15? No, it's not. So simply just stop here and I say in my notes, return the node. Yeah, so we're just going to return this node. And then, if you were to pass in null, like a node that's like this, well, what would happen? If you were to pass in null, null wouldn't go anywhere. It would just, again, just stop here. So you can kind of view our code as having two base cases. So base case number one. Okay, so these are the base cases that we could have for this. If we run into a node, like node dot right is null, node dot left is, or no, we'll see like node, right? So if the node we're looking at is null, we would like to return a new node of some data that we've passed in. So you can kind of look at when we're doing all this, we're looking at data, not looking at nodes itself. We're looking at the data 12, data 15, data 0, data 18, data null. Base case 2, it's not really a base case, but we need to handle duplicates in some way. Or like if you were to pass in null, this would simply just return null, or a node of null. So it would never get the opportunity to modify your actual tree, but duplicates now. So what we could say is if we have a case where duplicates return nothing, return the duplicated node. People tend to disagree on this. I've seen in textbooks both of these options. I kind of just like this one more. Just return nothing. Okay, cool. That is insertion. And then we have a little bit of code to go along with it too. So the next topic is deletion. And we could go over searching, but it's very straightforward. Same process as insertion, except we don't add in a new node or anything. If we find the node, we return it. If we get to null, return null. Okay, cool. Let's discuss this case deletion now. Let's go over some cases. So case 1, case 2, case 3. So we're going to analyze the tree deletion cases, and then we're going to apply this idea to a bigger binary search tree. Let's say I had 5, and then the left node of 2. And I simply want to delete delete 2. So case 1 is delete leaf node. So delete leaf, and I'm going to write 0 degree, right? Because it has no children. Well, then if we want to delete leaf, then we'll simply just get rid of it. So then this will become our new tree. That's case 1. Okay, case 2. I have 5. I have 2. And then I have 2 as a right child of tree. So I still want to delete 2. So I'll indicate this is the node we're trying to get rid of each version. This is another one to get rid of. This is another one to get rid of. But here we're trying to delete a parent with 1 child, so it will have a degree of 1. But in this case, all we do is, well, if in the real deletion, we probably check, we does not have a left child, have a right child. In this case, you have a right child. You'll simply just take the right child's value and then replace this 2 with it. So we go to that node that has 2 as data, replace its data to point at 3, and then we would do case 1. Now we can simply delete that old tree leaf. So it should go away now. Right, we can't have 2 trees in a tree. So we delete that, and then this will become our new thing. Okay. Moving on to case 3 of deletion. So I have 5. I have 2. I have 3. And then I have 1. Let's say on the right side I have 6. And then I have, let's say on the right side I have 8. And then here I can have 7. So this is a case, and we're still trying to delete 2. Right here, now let's change it up. I want to delete the big one, 5. Let's kill the root. So this is delete parent. It's still a delete parent only, right? Whenever you work with deletion, insertion, and the recursive algorithms, you're only focused on 3 nodes at a time. We'll have a degree of 2. We'll have 2 children. So in order for you to understand this, you have to go over 2 concepts called the in order predecessor. And then let's copy this. We talk about the in order successor. Successor. So what does that mean, in order predecessor? Well, and we'll talk about different tree traversal types, in order, post order, pre-order, in different video. But in order is essentially looking at a tree as sorted display, right? So if we're looking at our tree, which has 5, 2, 1, 3, 8, 7, if we were to sort that, we'd have 1, 2, 3, 5, 7, 8, correct? Let's see. 1, 2, 3, 5, 7, 8. Now, for right now, don't worry about how we got this pattern. Just know in order traversal results in you traversing the arrays in like this sorted fashion. So 1, 2, 3, 5, 7, 8. Now the in order predecessor, so we're looking at 5, right? Let's say we're looking at 5. The in order predecessor is the value that comes right before 5, which would be 3. And then the in order successor, okay, clear some things up, copy you, unclear some things up, and copy you. Right, okay. The in order successor of 5 would be then the element right after it, which would be 7. Okay, that's cool, but how does that look like on a tree? Well, if I were to just look at our tree here, but we have 5, we have 2, we have 1, 3, and I can probably just do this, and then just select this, right? It looks a little bit malformed. I'll just make that line better. Okay, right, this is our tree only. Well, we're in order predecessor is tree. How do you get that? To find the in order predecessor on a tree graph, we're simply going to go left. So go to the left child, and then right until leaf. Until leaf. So we're just going to go out left once, and then we're gonna keep going right until we hit a leaf node. Right? So 5, go left once, go to 2, then go right until we reach a leaf node. Well, tree is a leaf node. So we can stop here and we can return trees. Trees are in order predecessor. Successor. We're going to switch it. We're going to go right, and then we're going to go left. Left until root. And go right one, then left again. So we're going to only go right once. Now we're going to go left until root. Well, we're going to go left now. Right? This is the left node. Can we go left anymore? No, we can't, because that is the final node, or leaf node. Sorry, I don't know why I said root here. That's stupid. I mean to say leaf. That's my fault. Leaf. Okay, right and left till we reach leaf. Well, that's going to be 7. So we have an in order predecessor of 3 and in order successor of 7. What does this have to do with deleting the parent on a binary search tree? Well, what we do in a binary search tree is we simply, to delete 5, take either the in order predecessor or the in order successor and take whatever value is there, swap it with the value that we're trying to delete, and then just remove this entirely. So if I were trying to take uh, in order predecessor, you would see me, and here, let's make this like a blank node for now, because, 5 is not with us anymore. Alright, so if I was trying to do in order predecessor, I would take this true value, I'd simply move it up here, and then we could just delete this node. Right? So that would be handling deletion using in order predecessor. In order successor, I would take this 7, right? Right, and then we go left to find that in order successor 7. Plop that right there. Right, boom, and then we simply delete this node. So that is how you handle deletion in all cases. Instead, we could go over a big tree example. I don't think we need to go over a big tree example. Look, it's self-explanatory, but we will. Practice never hurts, right? But the cases are very simple. In case 1, leaf, delete leaf. Case 2, 1 degree, 1 child. Delete that node, replace, or not delete that node, replace the value of that node with the child, and then delete that child. Case 3, we tried to delete 5 that had 2 children. So we simply just took either the in order predecessor or in order successor and replaced the value. We didn't delete this node, we replaced the value at that node with the in order predecessor and in order successor, and then we deleted whichever one we took. So we took in order successor here, right? So we replaced 5 with 7, and then we deleted the in order successor node that was here. So if you really think about it, all deletion is simply just deleting the leaf node, right? What, here we delete a leaf node, then here we replace 2 with 3, then delete this leaf node. Then here we replace 5 with 7, delete that leaf node. So it all eventually is just simply deleting a leaf. Okay, let's go over a good example now. To get this formalized, I'm gonna make a big tree, and we're gonna do practice deletions, just like we did practice insertions. This is a very weird binary tree. I'll make this like 100. This can be 90. Or sorry, this can be 90. This can be 110. This can be 80. This can be 95. And this can be 7 or 85. This can be 92. This can be 91. This can be 93. 110. This can be 105. This can be 115. This can be 120. This can be 117. This one can be 106. And this one can be 107. So I have all my nodes here in the proper binary search tree order, left higher nodes to the right, lower nodes to the left. Now let's start off by deleting 100. So I want to delete 100 from this. 100 has 2 children, so we're going to find, I'll go with left in order predecessor. So we're gonna go left one, then right as much as we can. Left one, right. Can't go right anymore. We're gonna replace this 100 with a 95. So now, which node do we say we have to delete? Now we're really deleting this node. But wait, can we do that? No. Why? Because this node has a child, 92. What do we say when the node we're trying to delete has a child? We simply take that value, which would be 92 here, and fill that's an old node with it. So we're going to take the value of a child, child's value, and replace the parent's value with that. So just like this only. Okay, so we're simply going to replace this 92 here, right? And then that of course means the children will have to come with it. So let's simply just change this left pointer, point at 91's left child. Delete this. Right, we're not really moving the data. When we're saying replace the whole node and children must come too. So here we have a 91 and 92 at a right child. You'll have a 93. So sorry if I didn't make that point clear when I was talking about the cases. It's the whole node, not the data, that's being replaced. Alright, cool. Let's do one more example. Because that was a really big one. I feel like you got a lot from that. I want to delete 95. Let's delete 110. So I want to delete, and I'm sorry that I keep drawing it as a node. When you pass it in, you're really passing in the data 100 and then the data 110. And first we're searching to make sure the value even exists, and then we're going with deletion. Okay, 110. 110 found. 110 has two children, so we can either do the left, we can either do the in order predecessor or the in order successor. Let's do in order predecessor again. In order successor, just be right, left. There's nothing left here, place it to 115, and then bring this children up. So it'll be 115, left child 120, and then 117, right? I want to do right child because I did all of this for freaking in order predecessor here. So let's do it. 110, move to 105, right? We go left one, so we keep on going right. We reach 107. Let's take that 107 node. Any children it has no children. Nothing to worry about, nothing to add or implement. Let's replace this with 107. Now everything is good. Okay, let's go back. Let's do the same thing. I want to replace this with right, or I want to do in order successor. Go right. Can we go left? No, we can't. Take that 115 and its children and just shift it up. Right, clicking its node. What's a node after node? Its children. Those children come along with the node. So this will become 115, right? And we said, I'll just delete all this. 115 had a, what that's, that 115, okay, cool. 115 had a right child of 120. Which in turn had a left child of 117. Okay, so that was simply it. Now, I guess the hardest thing to understand deletion is when you're moving a node up, you are taking its children along with it. So we would take the children and we'd work like that only. Okay. Okay. So now that we've gone over some examples, gone over insertion, let's quickly talk about time complexities. So inserting is O log of n, and then deletion is O log of n. And we didn't cover searching, but searching is also O log of n. Because typically recursive patterns are O log of n because you split things into groups of 2, then split those things into groups of 2, and so on and so forth. Okay, so let's make this. The first thing I need is a inner class. I'm just gonna have a whole lot of data, a bit integer to mimic the tree that I was showing in the explanation. I need a left node, I need a right node, and then we need a constructor which will take in some data. Then need a root node, and let's say public this, 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 if that is equal to no. Let's do an insert now. So I want insert ideally to just take in data, but because insert is going to be done recursively, it needs to know reference to, so let's make it second. Just return this like that, and then we can go here, pass in node and into data. There we go. What are three cases? Left child, right child, or the same. So if it's a left child, if n dot data is is greater than the current data, then we're trying to pass in. We want our data to be the left child, so n dot left is equal to insert and current data. And well, what do we want to insert? We want to insert to the left. So I think the thing with recursion is kind of have to assume that your code works. I was watching a video on how to like easily do recursion, and that's pretty much what they said. Just like have a leap of faith that your code is gonna work. So that's how I'm gonna do this. And that we want it to equal to insert and that right like that. And this shouldn't be else, be else if. Okay. Else, so that means that the node kind of already exists. Let's return null. To signify that we just could not insert anything there. That should be fine because it's a node and stuff. It's not gonna actually mess up anything in our data, I don't think. Yeah, because we're not. Ooh, oh no, 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 it will. Because if look at it like this, right? If I'm passing in some data, then it goes here, but then oh no, the data is found. Gee whiz, what are we gonna do about this conundrum? I understand it. I'm gonna insert the node n. So essentially, when we found the data, because look, if I'm going to the left and I'm going to the left, and oh no, I match with the node, yeah, certain image, then it makes sense. Let's say that this is our tree. So I recommend it's like a white pen. Ooh, yeah, okay, cool. Okay, right. And then I'm inserting a node to the left. This is 10, this is 5. And then if I pass in 5 again, it's going to call this line, it's going to go here, trying to set it here, oh, 5 already exists, return null, and then boom, we've lost this 5 forever. That's actually not what we want, right? What do we want? We want 5 to just simply get returned back, so that way it'll still be the left child of 10. So all we're saying with this, that handles all of that. We need a recursion at end. Right now we have no base case other than if the node is found. We should also have one for if the node is null, right? What if we reach the leaf of a tree? Or if we insert a new leaf node, return new node comprised of this data. Alright, that's insert. And as you can see, it should be pretty easy. Why are we crashing now? Let me just take this, flap it here. Not the same effect, because what we said, if that's not true, that's not true, it is. And so we'll do the same thing either way. It's actually probably better, because then this will make sure that if the node is the same, it'll return that. And it'll just keep on, right? So like in that example we had, 10 would be less than 5, so 5 would be less than 10. We're trying to insert 5. 5 is not less than 5, we're going to return 5, and then 5 becomes the left child of 10. So everything seems to be working out. And I'm doing very simplistic diagrams. That was only 2 nodes. I think with recursion, you need to look at it very simply, because if your recursive algorithm works for simple things, it should work for bigger things. Right? That is the insert method done, I believe. Hopefully, I think it's right. It could be very wrong. I don't know. Let's do a node remove, and this is going to be in data. Well, we're gonna be searching. I'm gonna do recursive searching until we find the node. It's gonna look like this, essentially. Right, we're gonna keep on trying to remove, and then when we found the node, that'll be the one we remove. So, how am I gonna code that? Well, I think simply I'm gonna need to make a remove helper. So let me look at this simply. Remove. I want to remove 5. Find 5. So see, it's the left child of 10, and then we're going to delete it if it has, because it matches case 1. So that means we need to search. Then when found, case 1, case 2, case 3. So we can search simply just by doing this. Right? This won't do anything new or mess with our code in any way. And we can probably make these removes, because even though it looks like, oh, we're removing every node, we're not really. We're simply going to try and see if we can remove the left node, is what we want in this case, right? So work with it very simply, and that left equals remove and that left data, right? Assume your algorithm is going to work, right? So we're just going here to this left node, and we're going to try and delete it. Let's check. So if we've masked our data, that we're good. This is a node we're trying to remove. We're in the right place. Everything is good. Let's simply just remove this node, make it null, and then that'll update what it needs to update, and everything should work fine. And go to, so we're at the node, right? If we need to run the cases now, so I'll take all this. I'll plop those here. So when found, if n dot left is equal to null, and And that right is equal to null, so they're pointing to nothing essentially. And we're deleting, right? So that means its nodes are children, so we can just simply return null and get rid of that. That's fine, that's good. Case 2 is the one where null turn and that right. So we're simply just going to push and that right upwards. And that left. That should be case 2 done because it's going to update here because it's setting this. Looking complicating it a bit. Public node in order predecessor. T data. Sorry, we're not using generic. It's not data we're passing here, we're passing the node. Go node dot left. And it's equal to n dot left. While n dot right is not equal to null. You keep moving this until, well, no, we want this to be while n is not equal null, because this will actually skip the last child. It's not good. Let's say n dot right is equal to n, or n is equal to n dot right, and we should keep doing this. So this will give us the rightmost node, I'm pretty sure. Now we're going to return that up. So I want to remove the in-order predecessor. Right, because now we need to actually just kill this node off entirely. I'm being stupid. Let's just make this starting at predict. So we're gonna go here and we're just killing that node that has that. It's gonna evaluate to this case. It's gonna send it equal to null because our predecessor node has no children. We still have this call, and I want to set n to be equal to, or essentially we just want to return predecessor instead of returning null. Because when we have two children, when we're meeting the data, we're never actually getting rid of that node, right? We're just replacing the value that should be that node. Alright, so this should be the remove method. Do I want to add in a search method? Ooh, what should we do if none of these cases are met? Well, that just means that a node doesn't exist. Let's just return null, right? Oh, and it should be else if n dot right is equal to null. Now this code is reachable. Okay, cool. Actually, we're missing some things. Right? Okay, we need the base case of null. So if n is equal to null, return null. This is if we can't find the node. And the reason I thought we could put over here, but looking back on it, you actually need n. Why is that? Because we still need to do these updates, right? We still need to be able to, essentially we're like trying to look through the tree, right? Search the tree. We need to still return that node so that it's in the right place in its data. And then I keep doing this. This is stupid. This is never gonna give us anything, right? Then never actually updating anything. I'll say n dot left is equal to simply n dot left predecessor data. I think that's it. Oh, Jiminy Crickets! Jiminy Crickets indeed. Okay, I remember when we were talking about removal, we're just swapping the value around. Should be predecessor data. I have to actually double check this right now because I don't want to lead you guys astray. Or this is fine. Let's return. Let's do this. And um left should be equal to, or n dot data should be equal to predecessor dot data, and then let's return n simply, and then that'll be it. Okay, so why am I doing this line? Let's go over it. Let's explain it. Makes everything make sense. Case tree is the most complicated one, and I even just got it wrong a few times. Okay, let's go over it. So, what do we understand? Well, this line makes sense. I'm doing inverted predecessor. I need the inverted predecessor. Well, also, by the way, this should be end that right. Oops. End that right. I was right the first time. I don't know why I changed it. Because if we make it n is not equal to null, it'll keep going until n is equal to null, and we'll return null, which is wrong. We want to keep going until we have no more right children. The node that is the rightmost node is our inverted predecessor. So that's why we're going to in that right. We're going to keep on looping until we find that rightmost node. That's all this is doing. Excuse me. Let's go over case 2 a little bit more in detail. So that makes sense. Inverted predecessor achieved. I received it. Now why am I doing this? N dot left, remove n dot left predecessor data. What does that even mean? Well, firstly, the reason why I'm doing this instead of just doing predecessor dot data is because the in the removal process of okay, so let's go over n dot left equals remove n dot left predecessor dot data. This line might be a little bit confusing. Whenever we work with these trees, we need to follow the pattern. Like we need to go. I can't just remove predecessor and then call remove predecessor data like I had originally. Because think about it, is this gonna update any of the children, right? Like it's gonna update if I go to my example, right? This is a tree removing 10, replacing it with 7. So 10 goes away, 7 comes up. Okay, is that gonna update 5's pointer? No, not really. This we're gonna just be focusing on when we're calling this. Now the tree looks like this, and so we're getting rid of this value here. But in terms of the actual overall tree, there's still this, right? Because we said originally when we were inserting it, make this point to a node with a value of 7, right? So whenever we're removing things, if I just call that node from itself, now we're just looking at that 7 by itself with no connection to any pointers or whatever. So it'll have connection to its children pointers, but not to its parent pointers. So it'll go right here, but not here, because the parent pointer is still pointing at a node 7, right? These nodes themselves are not like um kind of like individual things that make sense. They're related by these pointers. You need to go follow the pointer path, right? That's what we did here. Although it was a lot more simpler insert, it's the same idea here only. You have to follow the pointer path, otherwise your pointers are not going to wire correctly. Okay, and that predecessor and then this last line. So the reason I'm doing this is because we need to update the data at that predecessor. So we need to update the data to the left node. Right. Oh yeah, and then this will be fine because we are going to remove the predecessor node, and our other cases are going to handle if it has a child. So then all we can simply do is just update the data, and then we should be fine. So then what we're going to do, we're going to turn that node, because like I said, we're not actually trying to delete that node. The one we're actually removing here is a predecessor node. This last return is the same idea as what we had this return. These end out lefts, these end out rights, they need a value. Need some value, right? We're going to ensure that they still have the same n. They still have the same n. Only when we're at a leaf node do we want to return the node data. Right? So what would happen is insert, boom, we're at the leaf, we're going down the tree, return that. Let's say that was the left child. Now that left child points to this node, then cool, now we can return that left child back up. So you're kind of seeing it's just recursion. Same thing here with the search, and the reason why we have this. And then I explained the cases, they're pretty straightforward. Now, also one important thing, the reason why we can't reference n directly is because n is a local variable and n doesn't actually mean anything in terms of the tree, right? So we really just need to refer to everything to these pointers as such. Now I can explain this. Okay, let's actually explain why the deletion code works. So first of all, let's go over what I am doing here with n.data, n.data. Let's go over insertion and then you can understand deletion. So we're going to simply insert 30 into this tree. Now where I say when we're inserting, we're looking at the data 30, and we're going to compare that 30 data value to everything. So this we can say right now is 30, and then this we can say right now is just the root. If the root is null, then we need to return the root and set it accordingly, right? But root is not null. The root is 10. We have a 10. So then is the data at 10 bigger than 30? No, it's not. Is the data at 10 smaller than 30? Yes, it is. So then we're going to try and make 30 the right child. So we're going to try and make 30 the right child of 10. And we're going to call that recursively calling insert. So now we're going to insert at this right value the data 30. So we're going to go here now to the right child of 30. Oh, wait a minute. Looking at this node, is it null? No, it's not. There's a value here, right? There is a 20 here. So we have to do this check again. Is 20 greater than 30? No. Is 20 less than 30? Yes. So let's simply try and insert 30 as the right child of 20. Okay, checking this again. Is n equal to null? Yes, there's a null reference here. So now let's simply insert 30. Let's return 30. And then so we're going to go back one up, right? So we're going to go here. This n.right of 20 is going to now be set to 30. Boom. Now this if statement evaluates, and now we can return this 20 node. Go one up again. Now, so we're going to say n.right of the root is going to be equal to 20. That is the recursive algorithm explained. Hopefully that makes sense. Remove. Let's go over this one. It's a little bit bigger. Let me just copy this. Okay, remove, right? This is my tree now. I have 15, I have 10, I have 20, I have 25. I will, and then here I can say I have like 4 and 8, 12. And I simply want to get rid of 25. I don't like 25. I think it needs to go from the tree. Okay, so we're going to start our root at null. So we're going to start with the root and we're going to pass in the data 25. So all of this we have seen already. We've seen this and then we've seen this. this is taken from this whole searching idea that we're doing here, right? We're searching for 20. That's all that is doing, right? We've seen it before, but I'll still trace it out. I'll still trace it out. Yeah. Okay, let's explain the case here, right? Okay, so we have 20. Sorry, I have to go away for a second. Is 20 greater than 15? Yes, it is. Go to the right. We're gonna see maybe 20 is the. Oh, sorry, I read this wrong. Is 10 greater than 20? No, it's not. Is 10 less than 20? Yes, it is. Okay, then let's see if we can remove this 20. I'm gonna go down here to 20. And I think I said 25. We'll do 20 for simplicity. Let's start with 25. Then we're gonna do 20. Then we can do 15. I'll cover all the cases. So we're looking at 25. Right, so we've looped is the data here. So now this won't be root anymore, right? What will this be? This will be 20. You know we're looking at has a value of 20. I'll just write 20. So is 20 greater than 25? No. Is 20 less than 25? Yes. So then we need to go to the right of that. Maybe the node, maybe this 25 that we're trying to delete is to the right of 20. Let's keep going. So now this is going to be the node 25. Our data is 25 only, so this won't go, this won't go, this will go. We would be in the else now. If 25's left child is null, right child is null, return null. Left children is null, right children is null, return null. So what does that mean? We're saying basically just return null. And then so going one up the chain where we said that the right child of 20 is this value, then we're going to return null and we're going to assign that to this right child. And then, so we'll have evaluated that and then we can return n, which would be 20, and then 20 will be assigned as the right child of 15. That's the first case. Now I'll do 20. Okay, same idea, only we're going to pass down 20 from the root. Okay, we found 20, good. So we're into this else. If 20 has no left child, we're going to try this first. If both of the children are empty, well that's not true. If 20 has no left child, which is true, then we want to return the right child. So what are we going to do? We're going to essentially return n.right. So what we're doing is we're bypassing this, right? We are going here at this value is 15, which is connected to 20. Now we're saying, hey, don't be connected to me, right? Because we're going to go back up. We're going to say whatever this is, set it equal to that, right? We're saying don't be connected to 20 as you were. Come here, be connected to this 25. And now you might be asking, how is 20 getting deleted? Well, now that nothing is referencing 20 anymore, the process known as garbage collection will just demolish it. Like it's over for 20, bro. Your life is cooked. So 20 will get taken by garbage collection. It's random one, but it will, right? And it doesn't matter because for the tree, 20 has no connection, right? 20 could be here for a billion years, right? But as far as the tree is concerned, we just said, okay, make that old right pointer of 15, make the new right child of 15 be 25, and ignore that, separate that connection to 20. And then 20 would still probably have its right pointer pointed to 25, like that. But I think it doesn't really matter because you can't really climb upwards on a tree. You can't do that. You can climb or on a binary search. You only go from root downwards. So because there's no connection downwards to 20, this upwards connection is utterly meaningless. So it's fine for us to leave that there. Okay, last case. 15. And I hope because I feel like the cases themselves aren't that hard. I think the recursion is what might trip you up. We're gonna jump into the else immediately, and we have two children, so none of this is gonna go true. Let's find our in-order predecessor, which is going to be 12. Let's remove the in-order predecessor. So can I say predecessor is equal to predecessor is equal to remove predecessor dot data? Let's see what happens when I do that. So I'm going to say predecessor is equal to remove predecessor dot data. Let's pretend that this said predecessor, right? Or well, and this is, yeah, let's do that predecessor. This is a little bit wrong too. This is saying n dot left. Okay, but either way, right? Okay, fine. Actually, let's leave it like this because this might make more sense. N dot left equals remove predecessor dot data. Right, that seems logical. And you told me we're traversing from the tree, so using pointers using n dot left, and the node we're trying to remove is predecessor's data. Right. So the tree is going to go n dot left. This will be set to predecessor's value of 12. The data is 12. And we are talking about this, so n dot left is what we're referring to. Okay. Is null, is null. What are we going to do now? Return null. Set that equal to n dot left. Fine. Right. Okay, this will have a value of null. This will not exist anymore. But wait, what about all of its connections? Well, its connections to its children will still its children will still connect to it, but it will have a connection to its children. And you eventually just kill the whole tree, right? So we do n dot left and left partition that data. And now look what happens. So we call in 12, we look for 12. So we're looking at, we go to n dot left, which is 10, so this would be 10. Is 10 greater than 12? No, it's not, so it's less, so we're gonna go to this right child. Call, ooh, it's equal, that's good. We're gonna set this equal to null. Then we'll update the right child's pointer to point to null. So then in that loop, we'll go down here, return n. Then it'll make sure that this left pointer points to 10. And also after that, okay, cool. So we've handled this, and the left is now set accordingly. Um, well, I still need this data, right? I need this data here. We're gonna simply update this data to be 12, and then we're gonna return n. So we're gonna return the node. So for our case, that won't matter too much, right? We're gonna return node. Okay, root node gets returned. Everything is good. But it's essentially doing the same idea as this one over here. Right, it's essentially doing the same thing. They're just making sure that your pointers get updated. Like you saw, the pointers were getting updated and staying on the right track. Because of this return end, this is going to do the same thing. Just when we happen to fall into this else, everything is returning something, right? No tree, a case tree. Okay, now that I think about it, we don't need him that much. I might just leave it in my code because even if this is not there, let's go to this one anyway. So now that we have that, we evaluate our code. I found some flaws in already. That's actually good at practice. I'll start doing that now. This is fine. This is an order predecessor. I don't think that's confusing. I'm going over this and this because it's confusing. Let's change this up a bit. I want this to be because if we have a and then return root. So what we're doing now is because what if the root is empty? Then we need this value to become the new root. And then return root. So that's what this is going to do here. It's going to say, okay, root's empty. Ooh, return that. Boom. Now we have a root. Here it's going to be like, oh, root. Root's already empty, or we find root wherever, regardless, right? If root's not empty, nothing will happen because remember this return end statement here is gonna make sure all the pointers are correct. unless we're actually modifying the value of root. But let's say simple case, root is empty. Call this initially, just find return null. Root's already empty, there's nothing to remove, it's already null. And that should be that. So this is the binary search tree in Java. I don't really know a good way to visualize it. Maybe I could code some traversal. Maybe in the traversal video we can come back to the binary search tree, and then we're gonna make other trees. So we can come back to those trees and we can actually view them. But that's going to be it for this video.